here is that when you looking when you're looking at this relation between the bilinear form S and the function of phi, then it is natural to consider the continuous duo that I said earlier. The reason is that this bilinear form induce so the bilinear form here induce a map called S bar from H to S star, and then using that inducing map we can formalize the relation between the functional phi and the symmetric linear form S. And the relation we see here basically is actually the image of that induced map is in the range of that induced map and some algebraic condition. So again, this is not a proof because the proof is a little bit involved, but I just want to give you some intuition behind what's going on here. We're trying to determine the relation between the bilinear form S and that linear function of phi. And the appropriate frameworks to do it is to looking at the Hilbert space, because in a Hilbert space, due to the real representation theorem, you can construct a map from the Hilbert space to its continuous view containing that phi, and in that way you can characterize the relation between S, the symmetric form S here, and that linear function of phi, and then you work out the details later. So that's the idea of this theorem. Now let me explain what it means to be nice. So again, so with the real representation theorem, S star can be equivalent in a product so that it is isometric to H, and S here is just the induced map from H to S star, as I said earlier. And so here, the way you construct the map is that for any U here, it maps to the bilinear form with U as the first factor. And now we have, so this is a map from H to S star. And then you have the range of this map, and you have its closure, and the closure is verified by the induced norm. And so nice here basically means that if it's nice, if it's not it's not one of the limit points inside the, if one of the limit points of the range of this induced map. So for example, if you have S here, if S here has closed range, then the set of limit points here is empty, and you don't really have to care about this situation. And actually, some people already look at that situation when the bilinear form is very special, like it has closed range, like. But our point of view is slightly different. We don't want to put any assumption on the symmetric bilinear form. We want to put assumption on the continuous, on the functional. The our mindset is that the symmetric bilinear form, it could be crazy, but the constraint normally in reality, the constraint normally come up from some um, logical reasoning. So the constraint should be something nice. It cannot be anything crazy. So that's why we would like to put the assumption on the functional, on the phi here, which modeling the constraint rather than on the bilinear form, because we would like to, our abstract framework to be applicable in many situations. So that's why we took that approach. And in application, the niceness here is actually not difficult to verify at all. It normally verifies via a Fredholm alternative. And you see where it comes from. The reason we use Fredholm alternatives here because our situation involves a bilinear form on some function space. So when we consider the induced map from the Hilbert space to its continuous deal, it is similar to consider a weak solution to some PDE problem. And so that's why the nice condition we're considering here is equivalent to a Fredholm alternative, which tells you about the solution, the weak solution to certain PDE problem. Okay. So that is the general abstract framework. Is there any question? No. So now let me discuss some application here. So we think that our abstract framework should be applicable in many situations. And the first situation we try to study in details is about capillary surfaces, because this subject is of great interest to not just mathematicians, but also people working in physics and also working in applied math and in some situation biology. So I think this is a great subject to apply our abstract framework. So capillary surfaces, where do they come from? They they could come from many situations, but I just give two examples here. First is a mixture of fluids. When you have two different fluids when you mix two different fluids in the same container, and then if the fluid don't mix into each other, then they gonna divide that container in two parts, and the interface is a capillary surface. Another example is the partitioning of a convex body. You try to partition a convex body in some optimal manner, and in such situation, the capillary surfaces also arise normally as a solution. So this is a precise mathematical capillary surfaces. So here you consider X here is an immersion from some abstract hypersurface into a ball in the Euclidean space. And certainly there's so many ways you could immerse such a hypersurface of n dimension into the Euclidean ball of n plus one dimension. And you try to minimize the area of functional here. So you try to minimize the area of the immersion given some condition. So capillary surfaces are critical points, and what it means is that, so here I'm just going to give the most general definition for capillary surface, which means you have constant mean curvature hypersurfaces. with constant contact angle. So the contact angle here is actually the intersecting angle, how the hypersurface intersect the boundary of the ball. And so basically here you have the critical points here arise by characterized by two conditions: constant mean curvature on the interior and the constant contact angle along the boundary. And that is expected because of the first variation calculation. So I didn't show you the first calculation variation. I only showed you the second variation calculation. But the first variation is similar in the sense that it involves an integration over the boundary and also integration over the interior. So when you set this first variation equal to 0, you get one condition over the interior and another condition over the boundary. So that's why the critical points here are characterized by two conditions: constant mean curvature inside and constant contact angle along the boundary. And the second variation, again, okay, I rewrite here. And you see clearly it is an integration over the interior and another integration over the boundary. And the index here is basically is just the index of this symmetric bilinear form on the function space, a smooth function. So here you consider a smooth function. And now we consider the type 1 constraint. So the type 1 constraint here is to fix the enclosed volume. And as I said earlier, this is equivalent to the consideration of UV with 0 average. And this also follows from a first variation calculation. And now the type 1 Morse index is the index of this symmetric bilinear form subject to type 1 constraint. So it basically the index Q on some subspace with the subspace W here is given by the following definition. You're looking at smooth function, but the integration is 0. So with 0 average. So clearly W here is subspace the original space of smooth function. And applying our abstract framework, our first theorem says that one Morse index here is equal to MIQ minus 1, even only if the following condition is satisfied. There is a smooth function U such that it satisfies, it is a solution of PD problems. And otherwise it is equal to MIQ. So the merit of this theorem is that it reduces the geometrical problem into a PD problem. And we had a lot of PD theory that we can get some information on that PD problem. Okay. So now let's see how I'm going to give the proof of this theorem because it's relatively easy. Oops. So I have only 5 minutes left. Is that correct?
You have 5 minutes, yes.
Okay. Okay. I'm going to try to wrap it up quickly. So the proof here, first, we replace the space smooth function here by a Hilbert space H1. And why can I do that? Because the space smooth function is dense inside this space, and it can be shown that the index doesn't change. And so that's why we could go from this space to a Hilbert space. Now, phi here is just given by the following. So phi of u gonna be equal to the integration of u over the interior of the domain. So you can think about phi here as the L2 multiplication by the function 1, the function which is constantly equal to 1. And phi here is nice because of the Fredholm alternative. You're looking at this symmetric bilinear form. The operator associated with the symmetric bilinear form is this elliptic operator, Laplace plus some fixed function p. So remember, p here is a function determined by the geometry of phi, so it's fixed. And so this is an elliptic operator. And then you can show that phi here is nice because of the Fredholm alternative, because phi here is just equal to the L2 multiplication by the function 1. So basically you, well, let me be a little bit more precise. The operator associated with the bilinear form here is Laplace plus p, and that acts on the interior and also the boundary derivative here. That acts on the boundary. So this is on the interior, and this is on the boundary. And so so here you see that the base, these two conditions right here basically corresponding to the case as a u equal to this function, this linear function of phi, when phi is given by this formula. And so phi here, another way to write down is this is 1 L2 interior and 0 L2 on the boundary. And so when you set up as of u equal phi, then you arrive at this PD. And the second, the last condition here corresponding to that condition that phi of u is smaller than equal to 0. So basically here the theorem here follows immediately from the abstract theorem we had earlier, just by interpreting the constraint accordingly. Then we have similar theorem for the type 2 constraint, and you can imagine that we're just switching the roles of the interior and the boundary here. And now the last theorem I would like to present is index estimate. So here the first two theorem here basically just reduce the index problem to some PD problems. Now the index estimate here, actually we use that PD information to gain more, to obtain more information about the index. So basically we obtain a theorem which characterize the case when the index equals 0, then in that case the surface here is totally umbilical. And when it's not equal to 0, when we're able to show that it's greater than some number L, and L here is totally determined by the geometry of sigma. And an interesting observation is that these results recover the previous results of Wang-Xi and Chao-Xie very recently as special cases. And also it is sharp inequality. And here in this remark, we just construct an example to show that the inequality is sharp. And then I have some open problems here if you're interested in knowing more about them. And that's it. Thank you very much for your attention.
Thank you very much.
Yes.
Could you come back again for the open questions? Just leave it here. Yeah. You still have 2 minutes to explain it.
So the first open problem is figure out what happens when the functional here isn't nice. So as I said earlier, from the geometrical point of view, the niceness assumption here is on the constraint, and normally when we consider some interesting problems, the constraint is nice, and so this is always applicable for geometrical application, for geometrical consideration. But from the functional analysis point of view, the abstract theorem is basically a functional analysis theorem. From that point of view, it rather intriguing to determine exactly what's going on when this functional isn't nice, when it's actually a limit point. And surprisingly, I don't have an answer to that question. So that's one open problem. Another open problem is to instead of considering just one linear functional, we can looking at two linear functional and consider the intersection of these two linear functional, and the point and the difficulty. Even though we assume that phi1 and phi2 here are nice, subject to the original consideration, when you consider phi1 and phi2 on some reduced subspace, it might not be nice anymore. So this is something to do with functional analysis, and it's something quite intriguing even for functional. I talked with a few functional analysis people, and they don't really have clear answer to this question either. So open problem 3 is somewhat easier. We instead of the ball, we could consider some other symmetrical convex bodies, and you could try to apply our abstract mechanism here for that situation. And at least the first thing is to determine the stable capillary surfaces in such situation. And I think this problem is accessible to graduate students because I think it's not too hard. And the last open problem is that show that this number L that we have in this theorem can be replaced by a concrete number. So in our theorem, L here is determined by the geometry of sigma, but we believe, or at least I believe, that L here in when we consider capillary surfaces, for example, L here can be replaced by a concrete number. So we can replace it here by some L here by some fixed number, and that would be an analogy to some theorem about minimal surfaces. Okay. And so these are some open problems that that are actually very interesting.
Thank you. Yes.
Hi, I have a question.
Yes.
Okay.
What in your theorem about type 1 Morse index, the Morse index with the type 1 constraint?
Mm-hmm.
What are the examples of surfaces that don't satisfy the condition? That there's no such U? Do you have any examples?
Yes. So actually, thank you very much for the question, because it allows me to talking about the example we have here. So here we consider the cylinder radius r inside the ball, and what we do is we just vary the radius here from 0 to 1, so that it is inside the ball. And what we learn is that for certain values of r, then there's no solution to that PD, so that the condition in that theorem doesn't satisfy. But for most value of r, the condition is satisfied.
Right, but this example, I mean, you're looking for a minimal surface, free boundary minimal surface whose CMC index is not the same as the, is the same as the minimal surface index.
Well, no. I'm not talking about the minimal surface. Here, I'm just talking about the index for CMC. So here, the cylinder here as CMC.
Right, but it doesn't have to be free boundary.
No, so here we consider capillary surface. So the contact angle here could be any
Right.
angle. It as long as a right angle, so it doesn't have to be free boundary.
Do you have any examples that are free boundary?
I don't. Actually, I don't. That's
Okay.
a very good question, but I don't. And I mean,
No.
for free boundary minimal surfaces, we don't know many examples, so that's why.
Right. Yeah. Okay. Thanks.
Thank you a lot for the question.
Any more questions? If not, let's thank the speaker again for a wonderful talk.
Thank you. All right. Okay, I stopped sharing, so that's the next thing. Okay.